This is not a 3D fractal. I know what you're thinking, it blatantly is a 3D print of a fractal and therefore it's a 3D fractal. But to be precise, and I'll hold it the right way around for the camera, maybe, everything's reversed. This is actually a 3D print of a two-dimensional fractal. I have taken a two-dimensional fractal and pushed it out into the third dimension. And it's interesting, and the way I built this was interesting. I didn't just take a picture of a fractal and throw it at a slicer. And I'll take you through my steps. There won't be a lot of code in this video, but I'll take you through the steps because I am on the quest to print a proper three-dimensional fractal. So this is Invalid Entry, and welcome to a Nerd Snipe episode. And by a Nerd Snipe, this is something that I've been looking at. It's been in my mind for a long time. I've been interested in fractals for since I was a little kid. My dad had a computer program that made fractals. He introduced me to the idea of a book on fractals, probably going back 30 years now, at least. In January, I spent a bit of time. I actually made a blog post. I will now swap to my scene view. I made a blog post. So this is my Jupyter notebook on this. As you see here, there's a whole bunch of things going back 2 years for some of the chaos things, a year ago for some other bits. Some of these are running 5 days ago, an hour ago, because I've opened them up to look at them recently. But I made this blog post in January, which basically was about taking slices of 2D fractals. So I've done a video back in January about fractals, about how you can calculate the different colours based on how long it takes for the calculation. So you iterate a calculation starting at each point. If it escapes immediately, you give it a value of 0. It escapes after one iteration, so 1, 2, 3, so on. So the ones in the middle never escape, so we stop counting at like 50 or 100 or whatever. So the difference, the fractal, is actually which areas never escape versus those which do escape. And the idea is that it gets very chaotic on the outside. So what's interesting about these particular fractals, there are other fractals. There are fractals which are not generated by computer algorithms or any algorithm. There are organic fractals as well. But these are the fractals I want to create 3D models on. And I started the idea of, well, I could change the formula on the third parameter as well. So I've obviously got two parameters, the XY axis. I have a third parameter. And as you look at the third parameter here, I was changing the power. I got these very alien shapes coming out here, which aren't quite right. People are used to this fractal, and then if I go down a bit, actually, this one is a power of 3 fractal, and this one's a power of 4 fractal, and so on. But you can actually have powers of intermediate values, of fractional powers, fractional fractals. And they look kind of alien, a little bit disturbing to me when you have these weird double-edged Mandelbrot, very strange things. But I wanted to know what it looked like if you put all these on top of each other. And to do that, I thought it would look like some kind of glassed cube where you have alpha values going in, so you sort of see the mist going in. So I built an isometric renderer. And the isometric renderer would allow me to basically build a cube out of little pixels, a bit like a Minecraft type of thing. Loads of maths about this, and I generated this. This was my very first three-dimensional fractal of all those slices put together, and it looked terrible. I thought it was going to look amazing. I thought it was going to be really interesting, but it doesn't. There's a lot of information here showing how that node sweeps round to the final position of the power 5, but it is the world's most ugly. And so the glass effect looked like when I put the alpha values in, because there's so many blocks, the glass effect basically just looks like a cylinder. You lose all the information, all the alpha values just lost completely. So I was thinking, I could actually then use this to generate a Minecraft or build those blocks in Minecraft, and I could go and explore them and sort of walk around and look at them. And I never really got around to doing that because of real life things. Anyway, so that was back in January. Moving on very rapidly to this month, when I started playing, or October when I started playing with them again, I realised that actually I needed a different way of doing the maths. So I was using Python, and the Python I was using here, make my screen a bit narrower, it was using the inbuilt complex numbers for XY coordinates. And I realised that actually there are other libraries out there which are very, very powerful. My mic's flickering a second. One of the libraries in particular is what they called quaternions. So I could basically take these out, this formula in the fraction corner, and throw it at something called the quaternion, which basically allows me to throw 4-dimensional numbers into it. So I did first of all, I checked it would work on the 2D plane where those extra values are 0, 0, and the code just takes it. The language, instead of taking complex numbers, I could throw in, these are all complex numbers here, but I could throw quaternions in and it would work nicely. When I first did this the first time, then I could then generate the 3D fractal, and using the isometric renderer, which I wrote back in January or even December, I could get my first glimpse at this 3D Mandelbrot. So this is a 3D fractal, unlike the one in my hand, which is just those height layers, the escape layers represented. This actually shows it looks more like a globe. So it's not actually the 2D fractal just rotated round itself, around the axis. You actually get individual nodes coming off here. So these little spiky bits here, they're not continually spiky. It's more like a crown. It's more like got spikes with little dots on the end. So these are actually, where you see here, they're not quite connected. They would be connected by a string which is smaller than the nodes I've grid. So here we have a point system. We've got the ability now of knowing. We've got, basically I said either it escapes before 15 or it doesn't. And if it doesn't escape by the 15th iteration, I put a dot in. It's that simple. This line here, by the way, seems to be infinitely small, infinitely narrow. So there is a dot there, but actually if you go a fraction off, that dot disappears completely, very, very rapidly. But I wanted to be able to 3D print one, and I thought, yes, this will look nice, be an interesting shape to do. Didn't know much about 3D modeling, don't know much about how to do this, but I know I could take a point cloud and build a model out of that. And this is where my troubles really started to begin, and I will share my progress. Okay, so the first thing I used was a thing called NumPy STS, which allows us to create meshes from it. And this is actually how I made this one. I made the 2D one, I gave it a Z coordinate, and it produced a mesh like that. You throw that into your slicer, and it would print pretty accurately. So I was overjoyed that this print, the bottom of it looks terrible, but the front of it now is pretty awesome. I now have a 3D printed fractal. It's very cool. It's very cool as a wall ornament as well, because as the shadows go across, as the light sun goes across the sky, the shadows on it change and it highlights different areas of it. So I think that's pretty cool. I also realised that my print head only has an accuracy of 0.4 millimeters, I think. So the accuracy of my print, or the accuracy of my model, I actually need to scale to the accuracy of this. This is a 10 by 10 centimeter print. Didn't take very long to print. Wonderful little output. All done in NumPy STS to actually generate the files. Because I only had a point system, the mesh worked really nicely. I actually had to generate all the vertices myself by hand in this one because I didn't understand what I was doing. But then I discovered Open3D. Open3D allowed me to actually generate individual points using this. This is my very simple thing. I'm using the formula, input times input plus constant, throw it into quaternions, use those Z indexes as the starting points, and then produce it, and I actually print off a progress as I go through it. Now the output of this produces a point cloud, and the point cloud looks something a bit like this. Let me open up the first point cloud first, this one. Now I don't know how well this will come up on YouTube, but there's a lot of points here. If you look at it from above, you'll see the Mandelbrot shape, but you've got all these internal points. And this is where the tooling and the meshing began to have a bit of a problem. When you start saying use the ball algorithm, whatever, to work out the faces on these points, or to work out the vectors on these points, what connects to what, the systems begin to have a bit of a heart attack and begin to die horribly. With more and more points, they get more and more pain. So what you really need is you need to get rid of all those points in the middle. And I did have an approach of doing that, which I have in Project One, where I have got rid of the internal points, and you've only got the points on the outside, or some of the points on the outside. I think I introduced a few more points, but the moment you have a point which is internal, it begins to have a headache. You can apply then alpha shape, so you can use the render. This is in MeshLab to use renderer. I do have a Python only version of it, and it does exactly the same thing, where basically it generates giant holes in the model. And depending on how many internal points you have, it generates either big or smaller holes. So the problem now is that I have all these holes, so if you throw this at a 3D printer, first of all, there's no volume to any of these faces, so it doesn't have any way of knowing how to generate the right volume. If you can get a solid body by increasing the size, but you lose all the detail. At the moment you increase the size of these joints and things, you lose the detail. So I basically need more surface points and no internal points. That's the key thing that we need to generate to be able to 3D print this. If you try 3D printing it and you've got a lot of internal planes, internal faces, what it actually does is it generates something like this. And I need to stress here, this isn't a mess on the printer. This is a lot of scaffolding holding up individual planes. So that anything straight in here is actually a face, and anything that's not straight is actually scaffolding. So the moment you try to remove these scaffolding, you begin to see the internal structure that it had generated. And this actually is a very fractal structure. So yeah, this is me taking it apart. And you see here, here's a part of the fractal it actually generated. It was these very, very, when I joined those points together, I didn't realize it had joined the internal shape together. So it made lots of tiny, tiny pyramids. And it's a valid fractal. This is a valid 3D printed fractal, but it was very, very fragile. There's lots of individual strands, there's a lot of stringing going on. So the moment I took the scaffolding apart, the entire thing just crumpled into a long bit of plastic extrusion. So I'm afraid it's one for the trash can. And that's where I am. I basically have a shape which is definitely fractal. I have a shape which you can begin to see here, for example, on the front here. You can begin to see that there is a crown shape going on at the front. So I'd like to continue this work. I'd like to look more at how to manage the 3D shape, how to go from the point cloud into that surface, that something that we can then bring into, you know, Fusion or Cura, and then go, yeah, just print that for me, slice it and print it. The other option I have been toying with is not actually skipping the model phase and skipping the render phase and going straight to calculating G-code, which basically means doing my own slices. And it may come to that. It may come to on every single layer that I do, work out the G-code to go to the next point is. But I don't know whether that's going to get the detail I want or whether it's going to generate something weirder with artifacts because of how those work. Whatever we do, we are going to have artifacts in because we're looking at a limited representation of the underlying fractal because we haven't calculated it to infinity. But that is what it is. And then there also is a limitation of what the printer can do about how these points are going to connect to each other. So yeah, that's where I am. It's a pretty short video for today. It is more of a progress update on fractals. I think they're beautiful. I think they're really interesting. I think they're really interesting how you go from a very simple formula, which is this that is basically the formula to generate the fractal for any location, just saying whether it escapes or not. The actual calculation there is all done in this one line. PyQuaternions are a really good library. It is a little bit slow. It's a lot slower than doing complex numbers, but again, you're actually multiplying the number of dimensions that you're doing the calculations up, so it's not surprising. And with a powerful computer generating, you know, a few 100,000 points, it doesn't take very long. The other thing is that because I'm printing a 10 by 10 centimeter, there is a minimum resolution of my printer, so I can actually limit the number of points I'm calculating for the resolution of my printer. Because anything more tighter resolution than that is just going to be lost when it prints. So that's it, really. That's all I've got for you today. Anyone has any ideas or suggestions or things they want to see, but programmatically going from Python source code and a mathematical algorithm into a 3D printed shape is actually of use in the real world. We're beginning to see things like in Fusion running algorithms to make shapes or patterns on a side. So you may have a side and you'd use an algorithm to actually generate the fill for that area to give it more interest, to give it strength. You use calculations and things like, just even for the scaffolding, you use mathematics and the calculator. So yes, this is how I want to generate my scaffolding. In fact, the new Cura has a new lightning infill algorithm to help infill at a much lower volume. So there are tricks that fractals will be able to help in generating. So if you can go from code into a 3D model, definitely the right way. For hobbyists like me, when you don't understand 3D modeling necessarily, I have been struggling, but I'm sure this is something that we'll work on and have some very, very cool output for. Anyway, that's it for today. If you enjoyed this, if you have any ideas or things that might help, or ideas of things you might like to see being modeled by code and then printed, please let me know in the comments down below. And I hope to see you all in the next episode. Thank you very much.